All right, mathletes, here we go. It's 4.4, logarithmic functions. So a logarithm is another way of writing an exponent and solving for an exponent. We'll use logarithms for solving with when our unknowns and our exponents, and that's going to be a useful tool for us. So y equals log of a of x. If it was written as exponents, we can see it can be written as x equals a of y. Notice the base of your exponent is the base of your logarithm. The answer to your logarithm is always an exponent. So we can see here's our exponent, and then we know that what you take your log of, x, is right in there, the argument of your logarithm. Okay, a cannot be equal to 0. We cannot have a base of 0, and a cannot be equal to 1. All right, so here we have a chart, and we want to make sure that we can go back and forth. If we are written in exponent form, we want to be able to write it in logarithm form. So here, this is going to be log base 2 to the 8th, and the answer to a logarithm is always 3. So log base 3, 7, 2, 9, our argument is the answer to your exponent, is equal to your power, 6. So then here we have log base 10 of 1 is equal to 0, our exponent. So log of 1/2 of 16 is equal to -4, your power. So log of a to the 24th is equal to a. Vice versa, we need to be able to go back the other way. So our logarithms need to be able to written as our exponents. So this is saying that 1/2 to the 3rd power is 1/8. 5, because of this 5, the 1st power is equal to 5, that 5. Okay. Log of 3/4, base 3/4 to 1 equals 0. So I have 3/4. The 0 power is 1. I have e to the -3 is equal to b. And I have 5 to 3 is equal to 125. All right, so we need to be able to go back and forth between our logarithms and our exponents. So that can help us find the exact values of the following logarithmic expression. Is our first step is we want to write it as an exponent, and these should be familiar powers that we should know. So I always let these equal to x. So then I'm going to say 1 over 32 to the x power is equal to 64. So in order to do so, I want to try and write things with the same base. So both these are factors of 2, so I can write this as 1 over 2 to the 5th. X equals 2 to the 6th. Well, this can be written as 2 to the -5x is equal to 2 to the 6th. Now that I have the same base, I can just say -5x is equal to 6. So x is equal to -5, 6. Okay. On b, I can see, all right, let this equal to some value x. So I can say 9 to my power x is equal to 27. Well, I can write this as 3 squared x is equal to 3 to the 3rd. So then I get 2x is equal to 3. So x is equal to 2/3. Okay. On C, I want to write this as 10. So this is equal to some x. 10 to the x is equal to 0.01. I want to think of this as 1 over 100. Okay. So then from there, I can do 10 10x is equal to 1 over 10 squared, and 10x is equal to 10 to the negative second. So x is equal to negative 2. And then on D, so remember that our radicals can be written as fractional exponents. So if this is equal to x, I get square root of 2 to the x power is equal to 8. Well, I can write this as 2 to the 1/2. X is equal to 2 to the third. Same base, so I have 1/2. X is equal to 3. Multiply both sides by 2, and I get x is equal to 6. All right. So the next part, when we're graphing logarithmic functions, the best way to understand these is to understand that the logarithmic function is the inverse of y equals e to the x. Notice, if we did our processes for finding inverses, we switch our x's and y's. So we get x is equal to e to the y. Well, now if I want to use this and rewrite it as a logarithm, I get log of x is equal to y. Let this equal now my f inverse of x. So this is the inverse. When we go ahead and graph them on our graph, we can see that they're reflections across the y equals x. Where here in the blue, this is y equals e to the x, and y equals ln to the x. And notice that ln to the x is just log base e. And so it's just a shorthand because it comes up so often, we have a ln to the x. Okay, notice the tables in our graphs here, that what was once our domain became the range of our inverses, and the range here became the domain of my log function. Okay, so knowing our things about inverses is going to really help us graph these log functions. Let's go ahead and see what that will look like. So to graph these, I want to first identify my parent function. So the parent function is y equals log of 3x. From this, I want to identify my inverse function. So my inverse function is going to be switching my x and y. So I get x equals log of 3y. And then I want to put it into my exponent form. So I know that this is 3x is equal to y. This is something that we just talked about in 4.3, so we should feel more confident in graphing this. So if we let our x's be negative 2, negative 1, 0, 1, and 2, then we know when we plug this in, we get 3 to the negative 1/2, or negative 2, that this is 1 over 9. 3 to the negative 1 is 1 over 3. 3 to the 0 is 1. And this was going to be 3 to the first is 3, and 3 squared is equal to 9. So if we know that these are inverses, if this is for 3x is equal to y, let's go ahead and find the inverse graph for this. So what was once my domain here becomes my range. So I have negative 2, negative 1, 0, 1, and 2. And then I have my 1/9, 1/3, 1, 3, and 9. So this is going to be the graph of my parent function. Let's go ahead and take a second to graph that. So I went ahead and graphed my inverse function in black and on my parent function in red of y equals log of x. So now if I want to graph this, because this is in my argument, this plus 5 is going to be a horizontal shift. So this is going to shift it left 5. So I can look at my graph and I can say, all right, I'm going to use the same graph. I'm going to change the color of it. And I'm going to take it. And I always kind of look at my y or my x or y intercept. So this was the intercept at 1. So if I'm shifting it over left 5, well now it's going to intercept at 4. Okay, where it's going to get infinitely close to that 5, but never ever cross it. Okay, so that's my function. So then if I want to now determine my domain and range and the vertical asymptote of my blue function here, I can say that the domain is going to be for all real x's such that x needs to be greater than 0, because it's going to have my vertical asymptote is at x equals negative 5. Before, on my parent function, the red function, that vertical asymptote would have been right here at 0, so that also shifts over left 5, so that becomes my vertical asymptote there. Okay, so now my range of my function, well, that's going to be similar here, that the range is for all real y's, and that's going to go down forever and up forever. And this should all make sense, because if we looked at my inverse function here, what was once, remember for the black function, that it was for all real x's for my domain. Well, when we do the inverse, that becomes my range. I don't have any restrictions with this. And then with the restrictions for your range, okay, come from your domain of your original function. So the restrictions now for this domain come from the black function's range. Okay, and that range had a limitation. So that limitation was for all real y values that y had to be strictly greater than 0. But that was just our parent function inverse, so it didn't have any shift in it. But notice that when we shift this over so that it's not that x has to be greater than 0, but x is going to have to be greater than this negative 5. So just like where this was 0, okay, this needs to shift over negative 5 as well, because it was a left shift. So the next one here, again, I want to look at my parent function. So the parent function here is going to be y equals log base 2 to the x, and that inverse function is going to be 2 to the x is equal to y. Because I know I need to switch my x and y's, so should do that step first, not to confuse anyone. So we get x is equal to log of 2 to the y. So then as I write this, so finding the inverse, switching my x and y's, so then I get 2 to the x is equal to y. So that is something I'm familiar with graphing with, so we're going to use that. So I have negative 2, negative 1, 0, 1, 2. So here I get 2 to the negative 2. Well, that is equal to 1 over 4. And then I get 1/2. And I get 1. And then I have 2. And then I have 4. Okay. So if I do my inverses, I know that my domain is going to become my range. So this is going to be negative 2, negative 1, 0, 1, 2. This is 1/4, 1/2, 1, 2, and 4. Okay, so I can go ahead and graph those, and I'm going to take a second to do that. So I went ahead and graphed my inverse function here in the black, and then I graphed my parent function here in the red. So now I can do my transformations. So my transformations, I can see that here in my argument, okay, that is going to shift left 3. Okay. The negative in front is going to flip it across my axis. So it's going to flip across the x-axis. Okay. And this 2 on the outside is going to shift up 2. As I do this graph, all this is actually going to be my blue graph. So if I take this, I can copy that graph. And from that graph, I want this one to be my blue one. And I'm going to first, I want to flip it. Up and down is my x-axis. So that's when it's just negative out in front. Okay, so what was negative will become positive, and it's going to reflect that way. Then I want to also see that my graph is going to go up 2. So again, I focus on this point right here. That is my y-intercept. So if it's going to go up 2 and it's got to go left 1, it's going to become, that same intersection point is going to be right there. And this should be, because of this one, should be a shift left 1. So as we take this graph, we're going to move it up 2 over 1. And that is going to be this log function graph there. Okay, so then again, now understanding the domain and range and vertical asymptotes. Okay, so because my domain is going to be for all real x's such that x has to be greater than, so it's typically greater than 0 for my parent function, but because I shifted it left, it's got to be greater than -1. Okay, and then my range, so my graph's off a little bit. I just moved it over a little bit too much. It should just hover there right before the -1. Okay, and then my range. So my range is going to be for all real y's, and that's going to be fine because it's going to go up forever and down forever on this function. And the last piece is my vertical asymptote. So vertical asymptote is equal to a vertical equation, so that's x equals, well, it was at 0, shifting over 1 is going to be make it x equals -1. So on number 5 here, if we're given some graphs, we want to do some matching. Best thing to do is kind of look for your parent function. So I'd identify that in 2 and think, all right, I need to find something with an intercept at 1, 0. And that's going to be this graph here, B. So this matches with 2. It's increasing. I know this is coming from my parent function. That would be 2x equals y, which would be something like this. Okay, so now that I got my parent function is b, and that's 2 matching up with, I can start kind of going through these other ones. So 1, I notice that it is just being added to 4. That's inside my argument, so that's shifting things left 4. So just like my asymptote here was at 0, I'm looking for an asymptote that's shifted left 4, and I identify that right here in A. So this is going to match up with 1. Okay. Log of 2x minus 4. So on this one, I notice that it's outside my argument, so it's actually going to be a horizontal, a vertical shift. So that's going to be my parent function just shifted down 4 with the same asymptote. So this is going to correspond to 3. Negative log of 2x of my parent function is again going to be a reflection across the y equals x. So I can see that this here is going to be 4. Okay. Well, c's got to be 5 here, but why is that got to be 5? Well, if I think about this, that the negative here, okay, is going to be a reflection. I can rewrite this as log of 2 of negative x minus 4. Okay, so this negative here is going to be a horizontal flip. Okay, so it's flipping it to the left. And then now, because we had to factor out the negative from both of those, we can see that it's not a shift left, but it's actually going to be a shift right 4. So we can see that C corresponds to 5. All right, last slide here. So if we're using these to solve equations, a lot of times it's going to be useful to go ahead and go backwards here. So if I have log of 3, 4x minus 7 equals 2. Using my definition of logs, I can say that this is saying that 3 squared is equal to 4x minus 7. Straight from my definition. Well, 3 squared is 9. That's equal to 4x minus 7. Add 7 to both sides, and I get 16 is equal to 4x. And I get x is equal to 4. Okay? On 2, I can do a similar type thing, and I can say that x squared is equal to 64. Square root both sides. And I get x is equal to plus or minus 8. Okay? Well, if you remember from our definition for logarithms that this a value here, a had to be greater than 0. So this negative 8 here is an extraneous solution. So x is only equal to 8 is my final answer. Okay. Well, C, notice it's as my exponent. So what I can do is if I rewrite this using logarithms, notice my variables in my exponent. So that's kind of our flag that just says that we need to use logarithms to do this. So if I do log base E 10 is equal to my exponent. Well, log base E, that is my ln. ln of 10 is equal to 3x. So I get my calculator out here, and I first can isolate my x and just realize, all right, divide this by 3, divide by this by 3. So I get x equals ln of 10 divided by 3. Well, I can type that all into my calculator. So ln's down here. So ln of 10, close my parentheses, divided by 3 is equal to, we can get an approximate answer here. X is approximately equal to 0.768. I can go ahead and test that and just show that E raised to the 3 times the answer I got should be equal to 10. All right, go ahead and highlight any questions you might have from notes tonight and bring them to class tomorrow.